Imagine finding out that about 1 in 5 people walking the earth right now are just completely missing an entire muscle protein.
Yeah, and the most incredible part is that they probably have absolutely no idea it's even missing.
Right, because it's not a disease,
Yeah,
right? It's just a mutation, like a microscopic typo in their DNA that completely changes how they run or how they lift weights.
exactly. And even how their bodies age over decades. I mean, unless you actually go out and have your genome sequenced, you just assume your body operates on the exact same mechanical rules as the person on the treadmill next to you.
Which is exactly why we are opening up the whole world of exercise genomics today. So, welcome to this deep dive.
Glad to be here.
Our mission today is to explore how our genetic code dictates our physical fitness, our athletic potential, and even our risk of sustaining structural muscle damage.
Yeah, it's a huge topic.
It really is. And we're pulling from two really fascinating sources today. First, we've got a comprehensive scientific review of the ACTN3 gene, which, pop science often calls the speed gene.
Right? You see that in headlines a lot.
Yeah, the speed gene. And second, we have this really revealing clinical study out of Brazil that looked at the intersection of two specific genes, ACE and ACTN3, in physically active older women.
And what's great about these sources is that we aren't just looking at what a good workout looks like.
Right.
We are diving into the mechanisms of why, like
Oh.
why your body might react entirely differently to the exact same physical stress as your workout partner, all based on these tiny microscopic genetic variations.
So before we get into the heavy biology of it all, let's just frame this for you listening. Is our DNA like a fixed blueprint for a house that we can never, ever change? Or is it more like a recipe?
A recipe.
Yeah, like where we've been handed the ingredients, but we can kind of adjust the cooking time and the spices through our workout routines.
I actually love that. The recipe analogy captures the reality of genomics perfectly. You really cannot swap out the raw ingredients you inherited from your parents.
Right, you're stuck with those.
Exactly. But how you train, how you recover, and the environmental stress you apply to your body, I mean, that dictates the final dish.
So to understand how those ingredients are functioning inside your muscles right now, we actually need to look backward.
I
Right?
too. Thousands of years backward, actually, to a rather bizarre evolutionary anomaly involving that ACTN3 gene we mentioned.
Okay, let's unpack the ACTN3 gene because this review details a mutation that fundamentally altered human history.
It really did. So this gene's primary job is to code for a protein called alpha-actinin 3.
Alpha-actinin 3, got it.
Yeah. And this specific protein is found exclusively in our fast-twitch muscle fibers, the type 2 fibers.
So for you listening, those are the muscle fibers you rely on for explosive high-power movements,
Yeah.
like sprinting to catch a bus or, I don't know, jumping to grab a basketball rebound.
Right. Fast-twitch fibers rely on... Okay. When a muscle contracts, microscopic filaments slide past each other to shorten the muscle. The Z line is basically the anchor point that holds everything together under that immense tension.
So the alpha-actinin 3 protein thickens and reinforces that anchor.
Exactly. It makes the scaffolding stronger for those explosive movements.
But the sources detailed this mutation that occurred in human history, known as the R577X mutation.
All right, kitschy name.
Oh yeah, very catchy. But in genetic terms, this basically created a premature stop codon.
Yes, it's literally a typo in the genetic code that tells the body to just stop building the alpha-actinin 3 protein altogether.
Just stop building it. Wow. So if you inherit this specific typo from both your parents, meaning you are what they call an XX homozygote,
Then your body produces absolutely zero of this explosive muscle protein.
which is wild, because in the vast majority of medical cases, missing a crucial structural protein like that results in severe muscle-wasting diseases, right, like myopathies.
Yeah, normally you would expect the muscle to simply fail. But alpha-actinin 3 deficiency doesn't actually cause a disease.
It just keeps working.
The muscle still functions, just with completely different architecture.
And the geographic breakdown of who has this mutation is staggering. I mean,
Yeah.
roughly 20% of the global population lacks this protein entirely.
Which is a massive chunk of humanity.
It is. But it's not evenly distributed. The review notes that about 25% of Asians and 18% of Caucasians have this XX genotype, meaning no protein.
Right.
Yet when you look at populations in Kenya, only 1% lack the protein.
And that geographic disparity tells an incredible evolutionary story. I mean, we really have to ask why a mutation that literally deletes a muscle protein would survive and spread to a fifth of the world's population.
Because usually a mutation that deletes something important gets weeded out, right?
Exactly. But the prevailing scientific theory here is that the XX genotype survived because it acts as a thrifty allele.
thrifty, like it saves energy.
Exactly. When early humans migrated out of Africa and moved into significantly colder environments like Europe and Asia, food became really scarce.
Oh, sure.
And in those conditions, generating body heat became a matter of life and death.
Right, because fast twitch muscle fibers, the ones that use this protein, they're energy hogs.
Total energy hogs, they burn through glucose rapidly and, quite honestly, inefficiently.
So in an ice age, having massive explosive muscles is actually a biological liability. You would just starve.
You'd starve very quickly. The sources explain that lacking this explosive muscle protein forces the muscle's metabolism to shift entirely.
So it offers enhanced metabolic efficiency.
Yes, and increased metabolic heat generation.
Yeah.
The body is just incredibly adaptive. Without alpha-actin 3 reinforcing that scaffolding, the body compensates.
How does it compensate? Does it build something else?
It does. It upregulates a different, closely related protein called alpha-actinin 2.
Okay, so it just swaps in a backup protein.
Essentially, yes. But this structural swap causes those fast-twitch fibers to actually take on some of the characteristics of slow-twitch endurance fibers.
Oh, wow. So they become more oxidative.
Right. That means they develop a better capacity to use oxygen to slowly burn fat and carbohydrates.
Which makes sense. I mean, in a freezing climate with limited calories, shifting your muscles to burn fuel slowly while generating more ambient body heat, that's a massive survival advantage.
It really is.
But wait, let me push back on this a little bit. If 1 in 5 people are completely missing this protein and they aren't sick, does that mean the protein is basically useless today?
Not useless, no.
Or is it kind of like having a car with a manual transmission versus an automatic? Like different, but they both get you down the road.
I'd say it's more like having a manual sports car versus a highly efficient hybrid engine.
Okay, I like that.
When you have the alpha-actinin 3 protein, you are driving the manual sports car.
Yep.
You have incredible torque and explosive power right off the starting line.
But without it?
Without it, your body swaps the engine for a hybrid. You are definitely not going to win a drag race, but you can drive for days on a single tank of gas.
That makes so much sense. And when you take those hybrid engines to the modern Olympic Games, the genetic divide becomes incredibly stark.
It really does. Which brings us to elite performance.
Right, because knowing that this missing protein creates this fundamental shift, the natural next step is to ask how this plays out when humans push their bodies to the absolute limit.
And the genetics completely dictate the podium here. Individuals with the RR genotype.
Wait, RR. That means they have the protein, right?
Yes, RR means they have the full expression of the alpha-actinin 3 protein. Those individuals completely dominate elite sprint and power disciplines.
Like, completely.
The scientific review noted that Olympic power athletes, so think 100-meter dash sprinters, Olympic weightlifters, they almost never have the XX genotype.
So lacking that protein is basically a biological roadblock for world-class explosive power.
Essentially, yes. The scaffolding just isn't built to generate that level of instantaneous force.
But the XX genotype, those highly efficient hybrid engines you mentioned, they have this massive shift toward aerobic metabolism.
Exactly. They have better fat and carbohydrate oxidation, and they actually clear the chemical byproducts of fatigue much faster.
So they are biologically favored to dominate endurance sports.
Yes, they are built for the marathon, not the sprint.
Okay, but here's where it gets really interesting, because the review highlights a major paradox here that completely flips the script.
Oh, the muscle damage data.
Yes. So the RR folks, the sprinters, they are built for explosive speed. You'd assume a drag racer breaks down easily, right?
That would be the logical assumption.
But the sources actually say the XX endurance athletes are the ones taking significantly more structural muscle damage during a marathon.
Yeah, they take a beating.
Why is the endurance muscle taking more damage during an endurance event?
It all comes back to the Z-line, that microscopic scaffolding we discussed earlier.
Okay, refresh my memory on how that works in a run.
Well, alpha-actinin 3 acts as a heavy-duty shock absorber. When you run a marathon, you aren't just propelling yourself forward. Every time your foot strikes the pavement, your quadriceps have to break your entire body weight.
Right.
This is called an eccentric muscle contraction, where the muscle is lengthening while under tension.
Running downhill is a perfect example of that, right? Like your muscles feel like they're being pulled apart with every step.
Because they physically are being pulled apart. Without alpha-actinin 3 reinforcing that Z-line anchor, the muscle fibers are structurally much more fragile under the repeated stress of those eccentric contractions.
And how did they actually measure that fragility in the studies?
The studies in the review measured this by tracking creatine kinase, or CK, in the bloodstream.
What exactly is CK?
CK is an enzyme that naturally lives inside your muscle cells. But when the muscle cell membrane tears or sustains structural damage, that CK leaks out into the blood.
Oh, so it's a marker for damage.
Exactly. And following marathons, half Ironmans, and even heavy jump training, the XX individuals consistently showed significantly higher CK levels.
Meaning more damage.
Much more. And they also self-reported much more severe muscle pain in the days following the event compared to the RR individual.
So you could possess the perfect genetic engine for metabolizing oxygen and running a marathon, but the actual chassis of your car takes much more structural damage along the way.
That's a perfect way to summarize it.
But that raises a huge question about overall injury risk. Like, does lacking this shock absorber protein make people more prone to serious season-ending injuries?
The data on injury risk is actually quite complex, mostly because the mechanism of injury changes based on your genotype.
How so?
Well, the review found that XX athletes, particularly in sports like soccer or ballet, they did suffer more severe ankle sprains and subtle joint injuries.
Okay, that makes sense if the joints are less stable.
The studies also linked the R allele, the power genotype, to a significantly higher risk of severe strain injuries.
Wait, let me make sure I understand the biology here. The R allele gives you the capacity for massive, high-torque muscle contraction.
Right.
So if you contract a muscle with explosive force, you're at a higher risk of literally pulling or straining the tissue purely because the engine is almost too powerful for the mounting brackets.
Yes. You generate so much force so quickly that the tissue just tears.
Whereas the XX injuries, like an ankle sprain in a dancer, those are happening because they lack rapid joint stability.
Exactly. Their fast-twitch fibers just aren't firing forcefully enough or quickly enough to catch a rolling ankle in time.
So the genetics don't give anyone a free pass from injury. They just dictate the specific mechanical failure points of your body.
Which is fascinating, really. Everyone has a weak point.
So we've covered ancient human migration, and we've looked at Olympic athletes. Let's ground this for the listener who just wants to stay healthy, avoid injury, and, age gracefully.
Absolutely.
This is where that clinical study from Brazil comes into play, because it takes these elite genetic concepts and applies them to everyday aging.
It's a brilliant study. The researchers took 70 physically active women, aged 50 to 75, and put them through 14 weeks of strictly monitored training.
But before they lifted a single weight, they swabbed their cheeks, right?
Yeah.
To establish their genetic baseline.
Yes. They looked at the ACTN3 gene we've been discussing, but they also introduced a second, equally critical genetic player,
The ACE gene.
the ACE gene.
And we really need to spend a moment on the ACE gene because it seems entirely unrelated to muscles at first glance.
It really does seem unrelated.
I mean, the ACE gene controls a system in the body that regulates bodily fluids and blood pressure. So how does a blood pressure gene impact whether you are a better sprinter or a better endurance runner?
It's all about oxygen delivery. ACE actually stands for angiotensin-converting enzyme.
Angiotensin-converting enzyme. Okay.
This enzyme plays a central role in the renin-angiotensin system, which basically dictates how constricted or relaxed your blood vessels are.
Okay, so it's a plumbing issue.
Exactly. It's plumbing. There are two main variants of this gene, known as the I allele, which stands for insertion, and the D allele, which stands for deletion.
And the study heavily focused on the ACE2 genotype, right? Two I alleles.
Yes. The ACE2 genotype results in lower levels of the circulating ACE enzyme in the body.
And what does that actually mean for the plumbing?
Biologically, it means their blood vessels remain more relaxed or vasodilated. And when blood vessels are relaxed, you develop a denser, more robust capillary network feeding into your muscle tissues.
Oh, I see. So more capillaries mean massive amounts of oxygen can be delivered directly to the muscles during exercise.
Precisely. And this highly oxygenated internal environment perfectly supports the development and efficiency of type I slow-twitch endurance fibers.
Wow. So the ACE2 genotype is kind of the ultimate genetic marker for endurance blood flow.
It absolutely is.
Conversely, having the D variant means higher ACE levels, tighter blood vessels, and potentially higher localized blood pressure. Right.
Right. Which might favor short bursts of explosive power like weightlifting, but it severely limits long-term oxygen delivery for endurance.
Okay, so going back to the Brazilian study, the researchers now had a complete picture of these women's genetic baseline for both muscular speed and cardiovascular endurance.
Right, they knew exactly what engines these women were running.
And then they split the 70 women into two very different workout routines. Let's talk about those routines.
Sure, so the first routine was called multi-component training. This was 90 minutes, twice a week, and it was highly varied.
Varied how? Like a boot camp.
Sort of. It covered cardio, strength, balance exercises, and agility movements. Very dynamic.
Okay, and the second group?
The second group was put into combined training. This was an hour long, 3 times a week, and it was a rigid 50-50 split.
50-50 between what?
Between heavy strength training on resistance machines and steady aerobic exercise on a treadmill or bike. Very structured, traditional gym work.
Got it. So when analyzing the results, the researchers categorized the women based on both the ACE gene and the ACTN3 gene.
Yes. For the ACTN3 gene, they specifically looked for the genetic markers that indicated whether the women actually had the alpha-actinin 3 protein or if they were completely missing it, like the XX genotype we discussed earlier.
And after 14 weeks, the physical adaptations were wildly different depending on the genetic profile, right?
Completely different.
The women who had the ACE2 genotype, meaning they had the relaxed blood vessels favoring endurance combined with the presence of the explosive alpha-actinin 3 muscle protein, they were the absolute super responders.
They really were. They saw the greatest health benefits across the board.
What kind of benefits are we talking about?
Well, in the multi-component training group, these specific super responders saw significant decreases in waist circumference and massive improvements in lower limb strength.
And the researchers tested that lower limb strength using the sit-to-stand test, right?
Yes, the sit-to-stand test, which basically measures how many times a person can stand up from a chair and sit back down in 30 seconds.
Which, I mean, that sounds incredibly basic compared to Olympic weightlifting.
It sounds basic, yeah.
But for a demographic of women in their 60s and 70s, the sit-to-stand test is one of the most critical clinical markers for functional independence.
Oh, absolutely. It measures the exact explosive lower body strength required to get off a toilet, get out of a car, and really to prevent life-threatening falls.
So improving on that test is a huge deal.
A very big deal. And in the combined training group, those same super responder genotypes saw better agility, lower diastolic blood pressure, and decreased overall body mass.
So they just had the perfect genetic recipe to adapt beautifully to the physical stress of the workouts.
Exactly. But the data also revealed a rather negative response for a different genetic group.
And this is the part that genuinely changes how we should view standard gym advice.
Eye-opening.
Because women who lacked the explosive muscle protein, the XX genotype, who were placed in the rigid, machine-heavy, combined training group, they actually saw an increase in their systolic blood pressure over the 14 weeks.
Yeah, their blood pressure went up.
Let's look at the mechanism behind that spike in blood pressure, because that seems so counterintuitive to working out.
Well, think about their muscular architecture. These XX women have a muscle built purely for endurance. They lack the thick Z-line scaffolding required to absorb heavy explosive loads safely.
Right, they don't have the shock absorbers.
Exactly. But the combined training program forced them to do heavy resistance machine training 50% of the time.
Oh.
When you put structural strain on a muscle that lacks the shock absorbers to handle it, the muscle struggles to adapt.
So what happens?
Because the muscular system couldn't efficiently handle the heavy loads, the cardiovascular system basically had to overcompensate just to push through the workouts.
Wow.
This overcompensation increased vascular resistance, which ultimately drove up that resting systolic blood pressure.
So it wasn't that the women were doing the exercises wrong or, not trying hard enough. Their cardiovascular system was literally undergoing a stress response because they were forcing a hybrid engine to do the heavy lifting of a diesel truck.
That's exactly what was happening. But the vital distinction here is that having the quote-unquote wrong genetic profile for a specific workout doesn't mean your body completely ignores the exercise.
Okay, clarify that for me.
Well, almost all the women in the study saw some level of functional improvement in their overall fitness, regardless of genetics. But the genetics dictated the ceiling of their potential adaptation.
Right.
And in some cases, like we just saw, it dictated negative side effects when the physical stress didn't match their internal structure.
This completely explains why one-size-fits-all fitness advice is just so frustrating.
It really is.
I mean, you could be doing the exact same 14-week boot camp as your neighbor. They're dropping waist sizes, lowering their blood pressure, and just feeling amazing.
While you are exhausted, your joints hurt, your blood pressure is creeping up, and you're seeing zero changes on the scale.
And society tells you it's a lack of willpower. But in reality, you are operating with an entirely different biological recipe.
Right. And knowledge of your own microscopic mechanics allows you to train smarter rather than just blindly pushing harder.
So if I know I lack the alpha-actinin 3 protein, I understand that my muscles are structurally more fragile under eccentric loads.
Right. Therefore, if you want to run a marathon, you must prioritize extended recovery times.
Because I'm taking more damage.
Exactly. And you'd need specific eccentric strength training to protect your joints because you know your body will leak more creatine kinase and sustain more micro tears than a runner who has the protein.
It's about tailoring your workout to protect your chassis while maximizing your specific engine.
Which is the future of fitness.
Which leaves a rather provocative thought for you listening to chew on today. Because as the science of exercise genomics progresses, the technology to sequence our DNA is becoming incredibly cheap and accessible.
It really is.
We are fast approaching a reality where the most crucial part of your gym membership isn't the equipment on the floor, but a cheek swab you take at the front desk.
We are undoubtedly moving toward an era of hyper-personalized fitness, where all the guesswork is just completely removed from the equation.
Imagine a near future where your entire workout regimen, like down to the exact rest periods between sets, the specific weight you lift, and the precise amount of eccentric load you take on, is strictly dictated by an AI algorithm reading your ACE and ACTN3 markers.
On one hand, it sounds incredibly efficient. I mean, no more wasted years doing workouts that spike your blood pressure.
Right, but it also introduces this really sharp, double-edged sword of genetic determinism.
Exactly.
Like, would this level of microscopic biological knowledge ruin the spontaneous joy of playing sports?
That's a great question.
If a cheek swab tells a 10-year-old they lack the structural scaffolding for sprinting, does that crush their Olympic dream before they even lace up their shoes?
Or, conversely, by leaning entirely into our genetic blueprints, could we unlock a level of human physical potential and longevity that we haven't even begun to fathom yet?
It forces us to ask whether we want to be told what our biological limits are, or if the struggle to find them ourselves is the actual point of the exercise.
I think that's something everyone will have to answer for themselves.
So the next time you hit the gym, and you're wondering if you're building a house from a blueprint or mixing a recipe, just remember that your biological ingredients were chosen thousands of years ago in environments you will never experience.
But how you bake that recipe today?
That is entirely up to you.